Hello everyone, this is the last part for our 2019 paper for Furthermath AQA paper. You did it, this is the last part. Again, make sure you subscribe to my channel and leave the comment if you want me to go over a specific question in specific exam paper. Here we have a mass that's attached to the spring, and then the tube is now filled with the oil. And let's think about what force would be applied to this mass and where it would move. So at the last sentence, it says it has been displaced above its starting position. So with that, we got a hint that this mass will move upward. So after time, the mass would go up like this. So your resultant force, F, should be always equal to ma. That's the definition of the resultant force. And let's think about what force imbalance would give you that resultant force of ma. First, there will be a gravitational force. Gravity always goes down, so that's a gravitational force. And that should be equal to mass and g, the gravitational constant, and that should be 10 meter per second squared. And also, it has a oil in it. Imagine you drop a ball into a jar of honey, then this viscous honey would resist the motion of the ball falling down. So it's that opposite. Now the mass is trying to go upward, but this has a oil filled in, so it has a resistive force that hinders the movement of the mass. That's against your resultant force, so it should go down like this. So oil resistive force. And in the question, it says resistive force has 6 MV Newton, where V is a speed. So this force subscript here, and that should be equal to 6 MV, where V is a speed. And now the most complicated one is your thrust. Imagine your spring is squished. Then what it naturally do is the spring will try to recover its original shape by going opposite of the compression. And in the question, it says compression, whenever it's compressed by epsilon meter, it gives the opposite direction of the force that has a size of 9 epsilon Newton. And here, whenever it's equilibrated, so force is balanced, nothing is moving, so mass is held rest in a position whenever it's above 20/9 meters. So imagine this dotted mass that I have drawn is a equilibrated position. Then it's saying that this height, whenever it is equilibrated, that is 20/9 meter. But in the question, it's saying that it moved up x meter from a starting position. So it means that this movement is x meter. Then what would be the height between the bottom of the tube to the initial position of the mass? Right? It's a subtraction of them. So the height of equilibrated point minus how much it moved up from the initial point. So that much of meter. And which direction should the thrust applied? As this spring is compressed downward, the spring is trying to move upward and recover its shape. Therefore, the thrust force should go upward, and that should be go upward. And here it says the equation is 9m epsilon, where epsilon is how much it is compressed from equilibrated point. So we found that it was 20/9 minus x times by 9m. So now we found all the forces applied to our mass. And then next step is to decide a positive and negative sign depending on which direction you want to make positive. So I usually use the resultant force direction as positive. So going upward is our positive. Then our resultant force should be equal to sum of all the forces applied. Then resultant force, which is our MA, should be equal to 3, because that's in the positive direction. We go upward as a positive, and subtracted by 1 and 2, because both are going opposite direction and going down towards the bottom of the tube. If you put all the 3 equations that we found, it becomes this. And we want to find x in terms of t. Therefore, we're going to change our acceleration, which is a, in velocity in terms of x and t. So remember your relationship between x, v, and a. V, which is velocity, is how fast your displacement is happening. So it's dx over dt. And acceleration is how fast the velocity has changed. So it's d dt of dx dt. So that should be equal to second order derivative of x. So for convenience, we're going to say this is x dot, and this is going to be x dot dot. So each dot represents one time derivative. Then this equation becomes this. And I used 10 here because in the question we said g is 10. So I substitute 10 into the last term. Then you simplify this differential equation. And then you divide everything by m. The question simplifies to a second order differential equation. And it is non-homogeneous because we have non-zero value on the right-hand side. So for this second order differential equation, you have a solution. You have a typical solution that has a form of e to the lambda t. Then your first derivative in terms of t would give you lambda e to the power of lambda t. And your second order derivative in terms of t should be lambda squared e to the power of lambda t. And then we substitute these 3 into your equation in your first line. Then this becomes this. But in order to solve this question, you first have to find what would be the answer for the homogeneous case. So for the homogeneous case, we need 0 on the right hand side. Let's first start from here, where right hand side is equal to 0. And e to the power of lambda something, or general exponential value, cannot be equal to 0, or it's always larger than 0. So we are able to divide through all the way through by e to the power of lambda t. Then the equation simplifies into this. We call this auxiliary equation. So this is your first step. You can do this step as I did step by step, or if you compare the original equation in first line and this auxiliary equation, they have the same coefficient. Second derivative has 1 as a coefficient, and you have 1 in front of lambda squared. Again, first order derivative, 6 is in front of it, and so you have 6 in front of lambda, and so on. Once you get your auxiliary equation, your step 2 is to find your complementary function. In your auxiliary equation, there can be 3 cases where you have 2 roots, r1 and r2, or 1 root, r1, and complex number. So you have imaginary number in your root. Say the roots are in the form of alpha plus minus beta I. In first case, you're going to have c1, which is constant, multiplied with e to the power of r1x, plus c2, another constant, multiplied with e to the power of r2x. And if you have 1 root, you're going to have the same thing, c1e to the power of r1x. However, in the second term, you're going to have c2 times by x and then times by exponential. And then lastly, if you have complex number, the real part becomes a exponent of the e, so e to the power of alpha x, all multiplied to c1 cosine. Here, the beta, which is the imaginary part of the complex number, will be multiplied with x, and then it goes into both cosine and sine. Let's see our case. If you factor our auxiliary equation, it becomes lambda plus 3 squared equals 0. That means our root is only single root, which is minus 3. And this is our case 2. So we called complementary function. We'll call this CF should be in the form of c1 e to the power of r1, which is our root, becomes minus 3. And remember, our equation was in terms of t, so we're going to put t here instead of x because we are dealing with dx dt, which is notated as d dot. So our t should go up to the exponent plus c2, which is second constant, and you have t here, and then e to the power of minus 3t. And that's your complementary function. And next step, which is step 3, is to find a particular integral. So it depends on how the right-hand side wrote. So if the right-hand side has a function of constant, meaning just the value or the number only, you're going to substitute y equals lambda. If the right-hand side is a first order polynomial, like 3x, and no higher power than 1, then you're going to substitute y equals lambda x plus mu. And if you have second order, you substitute lambda x squared mu x plus nu. As such, your pi should follow the order of your right-hand side function of your original differential equation. Now we have 10 in your right-hand side. If you go back to the first line up here, therefore our pi should have a form of just constant. So substitute y equals lambda. So what would be our first order derivative? It's gonna be 0. And also second order derivative should be 0 because constant derivative is just 0. So now we have a form of pi. We found all the derivative of our pi, and then we're gonna substitute this into equation square 1, which is our very original differential equation. Then it will give you 0 plus 9 lambda is equal to 10. Therefore, our lambda, which is our pi, should be 10 over 9. And this is our I. Our step 4 is to find our general solution. General solution is the solution with the constant. So we haven't found what that constant is, but we can find a general solution by adding our CF and pi together. So that, for our case, is just adding what I have squared, CF and pi. And our last step is to find actually what our constants C1 and C2 are. So you need to find what boundary conditions you have. But you can always start with when your x, in this case t, is 0. So what happened if our t is 0, meaning initial condition? So let's go back to our question. When t is 0, what is the displacement? How much did they move? None, right? It just released the spring, so it should be still 20 over 9 meters. So meaning it hasn't displaced, therefore it moved 0 meter. So in t equals 0, x should be 0. No displacement in the initial moment. And what else? When t is equal to 0, again, it's not moving. Therefore, their velocity should be 0. And velocity is your first order derivative. So let's apply our first boundary condition. Substitute t equals 0. And this general solution is equal to x, okay? So we're looking for x in terms of t. So if you substitute our first boundary condition into our general solution, e to the power of 0 all becomes 1. Therefore, the first term becomes c1 times by e to the power of 0, which is 1, plus c2 times 0, c1 times e to the power of 0, plus c2 times t is now 0. Therefore, that's 0, e to the power of 0, plus 10 over 9 is equal to x, which is again 0. Therefore, it simplifies to that c1 is equal to minus 10 over 9. So we got one constant from first boundary condition, but we need second boundary condition because we want to know our second constant as well. So our second boundary condition involved the derivative of x. So we're first going to find the derivative of our general solution, which will become minus 3 c1 e to the power of minus 3t. And the second term has multiplied two function. So we're gonna do product rule, where we're gonna differentiate t term first, then it becomes just 1. Therefore, we have this term left. And then we're gonna have another differentiation of e to the power of minus 3t. Then it will give you minus 3c2t e to the power of minus 3t. And then its constant, derivative of constant is just 0. So this is our differentiated general solution. And then we're gonna now apply the second boundary condition, which becomes c2 is equal to 3c1. There it is minus 10 over 3. So that's our c2. Now we found both constant here and there. We're gonna substitute this into general solution. Then we're gonna have specific solution, which doesn't have constant anymore. So that's our specific solution. 14b. If the question is asking for the damping cases, there are usually 3 cases, which will be equivalent to 3 complementary function cases. In part A, we've discussed 3 different complementary function cases, which are 2 distinct roots, 1 equal root, and complex number or imaginary roots. So for each cases has corresponding damping cases, where 2 roots it should be overdamped, 1 equal root, critical damping, imaginary roots, underdamped. Because for our auxiliary equation, which has a single root, we can say that our case is critical damping. Question 15. This question is about polar coordinate, which has r and theta. And first part, the part A, is asking for the gradient, where the gradient is defined to be dy over dx in the Cartesian coordinate. So we have to know how we can convert between the Cartesian coordinate and the polar coordinate. So for the Cartesian coordinate, we have x and y, which is more conventional. And then we have a polar coordinate, where we imagine a circle that passes through this point x comma y and then has a center in origin. So that circle should look like this. So here, the line that connects the origin and the xy point will be your r, and then the angle between the positive x-axis and that red line will be your theta value. If you zoom up this part, it will give you a right angle triangle. In this right angle triangle, we have adjacent length as x, and it goes up y amount, so your opposite should be y. And we're trying to get the relationship between blue, which is Cartesian coordinate, and red, which is our polar coordinate. In order to find the relationship between that, let's think about the definition of cosine theta. It should be x over r, adjacent over hypotenuse. How about sine theta? It is y over r, opposite over hypotenuse. Therefore, we can say that our x is r cos theta and y is our r sine theta. Just by writing this relationship, it will give you 1 mark. So make sure you remember that. So now back to our question, gradient. It is defined as dy dx. And the function that we want to prove has both r and theta. So we're going to separate our dy dx into dy over d theta. Now d theta is replacing dx, so we want to multiply d theta over dx, so that if you cancel these two out, brings back the dy dx form. And that means we want to find dy over d theta all over dx d theta. This is because that is equivalent to dy d theta divided by dx d theta. So first let's find dy over d theta. And we have y is equal to r sine theta. And r, don't forget, is also a function of theta. So I'm going to put this down to emphasize this fact. So you cannot consider r as just regular constant. That means we have to apply the product rule when you do the differentiation. So let's first differentiate the r term and then So what was the product rule? If you recall that if you want to differentiate both function f and g multiplied together, then you have to first differentiate the f and then multiply with g, plus now f is remained and g, the other function, has to be differentiated. So if you apply that to our case, then it becomes, how about dx d theta? And then what do we want? Dy d theta all over dx d theta. So you're gonna divide these two, which is exactly what the question is asking. 15b, it gives an equation for the polar equation r in terms of theta. And then here we have quotes b, which is given as a constant. And again, part b, always go back to part a, look for whatever information you can found useful. So from part A, we found dy dx in terms of dr d theta. So we get a hint that we might need a dr d theta. So let's start from there. Dr d theta, because tangent b part is just constant, we can just bring that in front of exponential when we differentiate it. So it becomes this. And then after that, we substitute into what we got from part A. So I copied and paste what we found from part A. When you substitute this, and also we're going to substitute r equals e to the power of quotes b theta also into our equation. Then our dy dx becomes all terms, both denominator and numerator, have exponential term. So we can cancel them out, and then the equation simplifies to this. Now we're going to use a definition of cotangent, which is cosine b over sine b. Then the equation becomes this. Whenever you have two angle terms, for example, in our case, we have both theta and b. Whenever you see this two angle, then it might be a hint to use your trigonometry identity. So from your formula booklet, you have these addition of trigonometry. Now let's try to make our form as close as possible to the equation given in the formula booklet. So let's multiply sine b to both numerator and denominator. Then the equation becomes this. If you compare the numerator, it's the first line, the addition of sine a plus b. If you look at the denominator, this is the form for cosine a plus b. Then your equation becomes this by applying these trigonometric identities. Then this is a definition of the tangent, sine over cosine. So everything simplifies down into tangent theta plus b. So let's see our diagram. This is a copy and paste from the previous page. What is a graphic representation of dy dx? So if you have a regular line that goes up to the right top, then your dy dx would be dx to the right and dy to the top. However, our equation is going towards left top. Therefore, this is minus dx, and that is dy. Let's call this angle alpha. Then what is the definition of tangent alpha? It should be dy over minus dx. From our derivation, we found that our dy dx is actually tangent theta plus b, right? So if you apply that, it becomes minus tangent theta plus b. And if you recall the relationship of the minus tangent and the tangent, let's say minus tangent A is equal to tangent 180 degree minus A. So if you apply this to our right hand side, then it becomes tangent of this. Therefore, we know that, and we've derived this, that tangent alpha is actually same as the right hand side. Then what would be the angle? OPT, which is the angle that question is asking for. Then it is 180, which is the sum of a triangle, minus theta minus alpha. If you substitute this alpha, then the equation will give you that OPT is actually angle B. Because there is no theta term in the OPT, we can say that the angle is not dependent on theta value.